Welcome all. I'm going to talk about the James Webb Space Telescope tonight. This is a picture of the spacecraft. Ain't it gorgeous, right? So, advance, please. So, basically, the talk is in three parts. What is it? What's it good for? And what's with the weird orbit? Because it's in a really weird orbit. So we'll start with what is it? So next slide. So it's a super expensive space-based infrared telescope. Super expensive means like $12 billion, way over budget, way behind schedule, but I think worth every penny in the long run. It's up in space because it's looking at infrared, and we can't look at infrared from down here. It's called a telescope. It really isn't. It's a whole observatory. It has a telescope in it, but it's also got computers and communication and propulsion and batteries and solar panels and all sorts of stuff. So this is a complete observatory that is going to function for decades with absolutely no human presence, which is absolutely miraculous. It's the biggest, most impressive robot that has ever been made. And $12 billion doesn't seem like a bad price for that. So here's two views of the James Webb. This is kind of like the top and the bottom, the cold side, the hot side. The side that the telescope is on is cold. The side that faces the sun is hot. This lovely piece of jewelry here is the primary mirror. It's covered in gold. This kite-shaped object below it is the sunscreen that prevents sunlight from warming up the cold side, and we'll discuss why it's cold later. This is a view from the bottom. The silver box down here is the actual spacecraft. That's what's got the batteries, computers, propulsion, attitude control, solar panels, refrigeration, and a whole bunch of machinery down here. And it's on the hot side. And you can see the layers of something like Reynolds wrap that make up the sun shields in between. This side faces the sun all the time. The telescope's on the other side, so it faces the dark sky where it sees the lovely heavenly bodies that it's after. Next slide. I'm just going to talk briefly about infrared just to kind of refresh everybody's memory from high school physics. Infrared is part of the electromagnetic spectrum, and the electromagnetic spectrum extends all the way from gamma rays and X-rays, ultraviolet, little window of visible light that we're really fond of, through infrared, microwaves, and radio. They're all electromagnetic radiation. They just vary in wavelength and frequency. The visible light was observed by the Hubble Space Telescope. It also saw a little bit into the ultraviolet and just a tiny bit into the infrared. The James Webb telescope has 4 cameras that cover a wide swath of the infrared spectrum. The James Webb isn't the first infrared telescope. There have been several other ones, notably the Spitzer Space Telescope, which was very successful. That was about 15 years ago. Next slide. Okay. Everything gives off infrared radiation, depending on its temperature. Hot things give off lots, cold things give off a little bit. This graph shows the brightness of the radiation given off, and this axis shows the wavelength. This is the same axis that was in the previous slide. So we have X-rays and visible light, window, infrared, microwaves, radios. Hot things give off lots of bright light. So for instance, the sun at over 5,000 degrees gives off lots of light and lots of high energy infrared. Things that aren't quite as hot as the sun, like say a human body, gives off a significant amount of infrared. That's why people feel warm. And that's why you can take infrared pictures of humans with no light, because you're taking a picture of the infrared that they're actually giving off from their body. Cooler things like say a star forming cloud down at 50 degrees above absolute zero give off less light, and it's shifted down towards the long wavelengths of infrared and would barely be visible by the James Webb. The sensors in the cameras are cooled down to 5 degrees, which is just like, that far above absolutely no temperature at all. And that's to prevent them from giving off infrared. Because if the sensors in the cameras were giving off infrared, the sensors wouldn't be able to see the object. It would be like having a light bulb inside your camera. It would just bleach out everything. And just for reference, the cosmos is 2.7 degrees. So if you go to the tiniest little bit of totally black sky in between stars, that's the temperature of the deepest space. Next slide.
What's the temperature of the array on the cold side?
The hot side is just slightly hotter than boiling water, and the cold side is about 27 degrees Kelvin. So the cold side is, some heat does get through the heat shield, and that heat gets radiated out to the 2.7 degrees of farthest deepest space. So the whole telescope is being warmed from underneath, from this top layer of the sun shield that's 27 degrees, and it's warmed up to 27 degrees, which doesn't sound very warm, but it's a little bit too warm for the sensor. There's 4 cameras in there, and they look at different parts of the spectrum, and it's just the longest wavelength infrared that needs the sensor that cold. So if the whole refrigeration system shut down, it would shut down one of the cameras completely, the most interesting one, but it would still be able to take pictures with the other 3 cameras. This is a similar situation with the Spitzer infrared telescope. It had a refrigeration system that was based on helium, had a tank of liquid helium that slowly evaporated over 3 years. And the evaporating helium was what cooled the sensors. And after 3 years, it ran out of helium, as expected. That was the mission profile. But it didn't stop. It just produced infrared pictures that didn't go to as long a wavelengths as it had previously. So, people say that, when the refrigeration goes, the Webb is dead, but that's really not true. It'll probably, limp along, producing a narrower spectrum of pictures for years to come. So because of the helium system is definitely has a limited lifetime. The designers decided to go to the more complicated, more expensive, potentially trouble-prone refrigeration system, which works really just exactly the same as your refrigerator, because it runs off light, not evaporating helium. So as long as the sun shines, the refrigeration system will work until it breaks, and then it won't.
What do you think it's gonna heat up?
Well, if the refrigeration system shuts down, then it'll heat up to 27, because that's the kind of refrigeration that the sun shield is providing.
When they orient when they look at another star,
Right.
do they rotate the entire platform?
Yeah, the telescope is not gimbaled on the platform. It's bolted solidly. So the whole thing's one block. So it's like someone with a stiff neck, if it wants to look over that way, the whole thing has to kind of reorient to look, which means that there's a limited part of the sky that it can look at any given time. Because if I'm the telescope and I'm looking that way, the sun's right down there. So I can swing around this way and everything's dark, and I can look up a little bit as long as the sun doesn't peek around the sunshade. Because if I look up too high, it's going to kind of look up my skirt here and warm things up. So the field of regard, they call it, is 360 degrees around and up and down about 20 degrees. So that leaves a huge area overhead that it can't look at. But it's going around in orbit. So if you wait 3 months, it's kind of traveled around, so now it can look at a different part of the sky. So eventually it can see the whole sky, but this is a limitation that if something really interesting happens, like, there's a supernova and everybody wants to look at it, and James Webb might not be able to, if it's depending on what part of the orbit it's in. And of course, it can't look down because the sun's down there. And if it tried to tilt towards the sun, it would be warmed up by the sun and glared out. And the other thing is that if it goes too far from its stable position, then all the antennas that are facing Earth wouldn't be able to communicate. They wouldn't be pointing in the right direction. The panels wouldn't be pointing in the right direction.
So it kind of brings true meaning to where the sun don't shine, right?
The sun don't shine there. Nope. No. No. And when the telescope repositions, it takes a while for it to settle down because there's rocket fuel in the tanks and it's liquid. And when the telescope moves, the fuel starts sloshing around, and it can take up to 20 minutes for the sloshing to die down, because otherwise the telescope's jiggling as it's sloshing. And this is kind of a problem. They've tried in the past. They've tried baffles and filling the tanks full of stuff, but it's a real problem having a container of fluid in zero gravity and trying to draw it out, because normally a tank, the liquid always goes to the bottom, so you have the fuel line going into the bottom of the tank, but in space you don't know where the fuel is going to be. It might go off and kind of in a blob on this side or that side. So it's quite a design problem getting rocket fuel to the intake at in zero gravity. So when a spacecraft kind of stops, like turns its engines off, it has to be designed specifically to be restarted. They have to do something like have a little tiny rocket that'll start pushing it so that the fluid sloshes to the back of the tank so they can suck it up and fire up the big rocket. So it gets complicated. So is this is my next slide here, is it? Can I? Okay, back. So we talked about the sun shape. Sun has lots of energy coming out. 95% of it hits the first layer and bounces off, but that means 5% gets absorbed by the layer. So it warms up to like more than the boiling temperature of water. And it radiates infrared, which goes and hits the next one. 95% of that bounces back again, but some of it does warm it up. So that the infrared kind of like bounces along until it leaks out the sides between the layers. And it just gets colder and colder until you get to the cold side. Dare I ask for the next slide? Yeah.
The orbital radius of this satellite is roughly that of Earth, is it not?
We'll go into that in nauseating detail later on in the talk. So big mirror. It's in segments because it's so big they couldn't make it in one piece. It'd be ridiculously heavy and probably not physically possible to make it that big. So it's in small light pieces that pile together, coated in gold because gold is pretty, and it reflects infrared very nicely. Now, astronomers love big mirrors for two reasons. One is they gather lots of light so you can see dim things. And the other is that a lot of telescopes are limited by aperture diffraction. When the light comes into the aperture, it bends, and that spreads it out and blurs the image. The larger the aperture, the less diffraction there is. So because the JWST is so big, way bigger than Hubble, you would expect it to have phenomenal resolution. Ain't so. Next slide. So this is the only slide that has numbers on it, right? I hate blue slides with yellow numbers on them. This is the only one you'll be subjected to. So what it is, I listed 3 telescopes here: Hubble, JWST, and our beloved Celestron 14-inch. The optical resolution of the Hubble is phenomenal. JWST, boy, you won't write home about that. And in fact, it's in kind of the same ballpark as the Celestron. It has an enormous mirror, 33 square meters, so it can catch a huge amount of light and take pictures of very dim things, but can't make a really sharp image. And the reason is because of the wavelength of the light that it's focusing. The diffraction depends not only on the aperture, but also on the wavelength of the light that's going through the aperture. So longer wavelengths, more diffraction. So yeah, it's a great telescope, but that is kind of its weak point. It's not quite as spectacular as we wish it was. Can't do anything about the physics. Next slide. And because it's big, I mean, you'd have trouble parking it in a tennis court. That's how big it is. Like it wouldn't fit in here. And it has to get folded up to put on top of a rocket. So here it is, all scrunched up, and on top of the this Ariane rocket that's taking off from South America. Wait a minute, did he say South America? NASA entrusted its baby to be launched from South America? Well, yes, it did. It launched from French Guiana for two reasons. One is that the closer you get to the equator, you get a little boost from the rotation of the Earth. Also makes it a lot easier to get into equatorial orbits. But the other thing was that it was Ariane that launched it, not NASA. They're from the European Space Agency. And hats off to these guys because they just did a bang up job with this launch. Because it was so far behind schedule, they had a whole decade to collect the very best parts that came through, and they put them all on a shelf and saved them to make this rocket. So when they tested a part, say it was rated for 100 plus or minus 2%, if it was plus or minus 0.5%, ooh, we saved that one for James Webb. And they put together this phenomenal rocket that was such an accurate launch that the little rockets in James Webb didn't have to use the fuel to correct the last little fine tuning. And as a result, instead of 10 years of service, we're going to get 20 years of service out of the telescope. So hats off to the guys at and girls at Ariane. So this is what it looks like when it's unfolded, and then hopefully the video will show it to us as it unfolds. Maybe not. Okay, so back to the telescope part. The astronomers will recognize this. Light comes in, hits the primary mirror, bounces back, hits the secondary mirror, bounce back, and then there's a couple of little extra little mirrors here, and then finally the focal surface back behind the main mirror. These are all the little segments that make up the main mirror, and they're all individually pointable and also distortable, so they can be tweaked and bent and cupped and change shape to fine tune them. So when it was deployed, each one of those mirrors individually had to be tuned after being rattled around in the rocket. This little mirror there is the fine aiming mirror, because as I said, the whole spaceship has to point at things, and it's hard to get something that big and heavy pointed exactly the right direction. So this little mirror is mobile, and it can correct for the last little pointing error. The focal surface is where all the instruments are, and the next slide has the instruments, and this looks very confusing, and it is. So here's the light coming in, bounces off a mirror, goes through a beam splitter. So the short wavelengths go this way, long wavelengths go that way, and they end up in these two cameras. Each camera has two sets of sensors, so there's a total of 4 images being taken at 4 different wavelength ranges. And there's filter wheels, so they can narrow it down to an even smaller section of the spectrum. And there's also a spectrograph and other things that I don't know what they do. So there's lots of very fine instruments in there that make great pictures. Next slide.
Would this all be kind of underneath the shield, or is it still above the shield?
Oh, this is definitely above the shield, because that's the stuff that has to be kept super cold. And it's right smack up against the back of the mirror. And the refrigeration lines, the refrigeration unit is in the spaceship, the hot part. And the refrigeration lines run up, and they just go to one camera. They just go to the long wavelength one, because that's the one that has to be cooled down as much as possible. So that's what it is. What's it good for? There's three things that it's really good for. One is that it sees through dust. Imagine if my fist is a chunk of dust and light comes along, light's got a really small wavelength and it goes clunk and hits the dust and doesn't go anywhere. Infrared comes along, infrared's got a great big huge wavelength and it just goes right around the dust because the dust particle is smaller than the wave is. So good for looking through dust, and we'll see some real nice pictures of that. It can detect chemical composition of things far away, which is really interesting to the astrophysicists. And it can look far back in time to galaxies far, far away. So first we'll look at the dust end of things. Next slide, please. So this is not a positive and negative photograph. This is a light photograph, and this is an infrared photograph. So they're taken at two different wavelengths. The plastic garbage bag here represents the dust. It's opaque to visible light, but it's transparent to infrared light. And what's also interesting is you look at his glasses, look at plastic lenses. These lenses are transparent to visible light, but opaque to infrared light. So, you know, if somebody asks the question, well, which is better, Coke or Pepsi? It's not that one is better than the other, it's that they're showing different things, they're showing different information, so they give you a larger picture of what's going on rather than just taking part of the information. Next slide. And this is an example of the magic of looking through dust. Here we have Messier 74, which has the reputation of being a very dim object. Hubble photograph, Webb photograph. If you look at the center of the galaxy, there's almost no visible detail in here because of the dust and light scattering. Through the Webb, the same area, there's a phenomenal amount of detail that now becomes apparent. And the center photograph is a morphing of the two put together, the miracle of image processing. But it gives you an idea of the difference between what one telescope and the other sees and how put together they give a much richer picture of what's out there. Next one. And this is so gorgeous. This is worth 12 billion bucks just on its own right. I mean, this is so gorgeous. It just leaves me speechless. So this is me speechless because it's so gorgeous. So this is a bunch of dust and stars being born, and obviously the light is having trouble seeing through the dust, and Webb comes along and just like powers right through it and sees structures and objects that aren't apparent. But once again, is one better than the other? No, there's like chocolate and vanilla, Betty and Veronica, you know, life is rich. So next one. This is a not so spectacular photograph of the Carina Nebula, which is right next door to what we were just looking at. And I just wanted to point out this object, which barely shows up in the light photograph. And look at this one, it's the brightest thing in the sky. And that's not because it was behind dust. I mean, it is behind dust, but it's redder and its light was not apparent to Hubble. So your Webb can just see things that Hubble couldn't see because they're radiating in a different part of the spectrum. And this area down here is a good example of the magical looking through dust effect. So we can look forward to decades of, you know, spectacular photographs. Next. This doesn't have the same wow factor, but in fact, it actually tells us more. Chemical composition. This is a spectrogram of the atmosphere of this planet, which is 200 light years away. It's orbiting around another star. It's got the name of WASP 39b for some reason. And as it passed in front of the star, James Webb took a spectrograph of its atmosphere and determined that it had sodium, water, carbon monoxide, carbon dioxide, sulfur dioxide, and I think there's something else in there too. This is phenomenal. This planet is 200 light years away, and it's telling us what molecules are in that atmosphere. So like I say, it doesn't make pretty pictures, but it sure tells us a lot about how the universe works. Next slide. And this one, I apologize for not being able to tell you exactly what it is. I didn't keep the reference, but this is a light photograph and an infrared photograph of the same upper atmosphere of the same planet. And I can't remember which one it is, whether it's Saturn or Jupiter. It was taken by an early satellite. It wasn't taken by Hubble or James Webb. But it shows you that the added information that you get from infrared gives you information on temperature and chemical composition, and areas of the cloud that look uniform in visible light are obviously very different in some way. And if you're smart, you can figure out why they're different. Next one. Okay, this is a long time ago, far away part. Hubble photograph, deep field photograph. What they did is they gave Hubble a job. They said, we're going to give you 2 weeks off, and all you're going to do is stare into nothing for 2 weeks. And they gave it a tiny little piece of sky about that big, totally no name, black hole in between stars that there was nothing of interest that they knew of. And they just said, just look at that and get as much light as you can and see, look as far as you can and see what's there. And Hubble came up with this photograph. And these little smudgy things are not stars, they're galaxies, right? The sky is just like totally full of galaxies. And these are really old. The telescope's looking back in time billions of years. So that's early universe and early galaxies. And the astrophysicists are really interested in those early galaxies because we're trying to figure out how the universe formed. How did those galaxies start, the very first ones? Because they're quite different than the ones that exist now. So Hubble did a good job of that. And when Webb was launched, one of the first things that they asked it to do was to go back to exactly the same spot and take another picture. And this is what they got. And if you're doing the Coke and Pepsi thing, you know, 4 to 5 people will pick Pepsi. There's a much greater range of objects that it's seeing. And all these colors are artificial. They're put in by the image processing, but they're different. They're coded as different colors because they're different parts of the spectrum. So we're getting information about the spectrum that's coming from these. Can you get the next one? And these are the same photographs, but with little yellow arrows added. And I want you to look at these 3 objects here that completely don't show up in Hubble's photograph because they are so redshifted that they're just outside the range that Hubble can see. And they're also so far away. They're like the oldest galaxies that we've ever got photographs of. Now, at this point, you might have experienced some confusion about what is this redshift and this old galaxy thing. So I'll talk about that a bit. Next slide. According to the dogma, in the beginning, there was a big bang, and the whole universe was squished down into a little thing, and it went boom, and everything flew out, and it's been flying out for 13 billion years. And the stuff that goes faster has gone farther, and the stuff that was slower hadn't gone as far. And if we're way out here and we look back towards the beginning of the universe, we see very old galaxies because it's taken a long time for their light to come out, and the light's kind of been chasing us out, and it eventually caught up so we can see them. But that light left billions of years ago, so we're seeing an image of galaxies that are billions of years old. Now, if you kind of take this story, you think, well, okay, well, where is this? Where is the center of the universe? Like, which direction? And if we want to see these old stars, don't we have to look at the center of the universe because that's where they were? And the answer is really kind of disturbing. No, because we are at the center of the universe. We're just like a 2-year-old. But so is everyone else. every other galaxy is at the center of its universe. And in fact, you go anywhere in the universe, like for instance, to the next slide. And the view from everywhere is the same. Everywhere you look, you see those fields full of stars off in the distance. Everywhere you look is towards the center of the universe, the Big Bang. So every direction that you look at, pick a random direction, look far enough, and you will see early galaxies. And because there's so much relative motion, the light's been stretched out and it's been shifted way down into the red, so we have to look at infrared to see them. Even though that light was originally visible light, now it's been shifted down into the infrared. So there you are, we live in a galaxy full of 2-year-olds. Next slide. Okay, now we get to the orbit, right? This stuff is here. General layout, Sun, Earth. James Webb's orbit is a circle around the L2 point. Now, you may not have heard of the L2 point, but you're sure going to hear about it tonight. So what happened was that the James Webb was launched from Earth. Here's the separation from the launch vehicle. So the launch vehicle just gave it a big boost and then fell back. And James Webb fell all the way, just like a baseball going through the air, all the way up 1,000,000 miles and did this loop and ended up in its orbit. And it stays there, which is weird because the Earth has gravity and the Sun has gravity, and they're both pulling on the on James Webb. So why doesn't the James Webb fall back and smack into the Earth, or zip by it and smack into the Sun? I mean, that's what gravity is trying to do. Herein lies the mystery, which shall be explained. So next slide. Oh, great. Okay. So here is a video of this circular orbit around L2. And then the point of view changes so that we're looking at it from the L2 point through the Earth to the Sun. And there's James Webb orbiting around in its place. And if you can, you could actually see this if you had a good telescope. It's possible to see James Webb with a very good amateur telescope. And if you went out at midnight every night and stood facing south and looked at the anti-solar point, which is the opposite of where the Sun is, midnight, so the Sun's down there, anti-solar point's up there. And James Webb is about 20 degrees from the anti-solar point. And if you come out every night and watch, it will do a slow march around the anti-solar point. It will take 6 months. The celestial sphere is zipping by because the months are going by. But this orbit isn't moving with the celestial sphere. It's staying still in relation to the Earth. That was really weird. Next slide. So after hearing this, you might have some very valid questions, like, where is this orbit? And why was James Webb put there? And what is it orbiting around? Because there is nothing at L2. If you were up in space, right there in a spacesuit, and that was L2, you could, there's nothing there. There's no little pocket of space dust or asteroids or anything. Why is it in an orbit around L2? If L2 is so great, why not put it at L2? This will be answered. Why isn't the orbit, the orbital plane, the same as the ecliptic? Because all the objects in the solar system are going around in orbits, and they're all basically in the same plane in the ecliptic. All the planets are, all the asteroids are. So what's with this orbit that's standing up at 90 degrees to everything else? Why isn't the L2 point at the focus of the ellipse? Because the orbit's actually an ellipse, and elliptical orbits always have the primary body at one of the focal points, not at the center. But this is at the center of the ellipse, breaking rules. And it's called an unstable orbit. Well, aren't orbits supposed to be stable? Isn't that the definition of an orbit? And can we get there to fix it, like Hubble? So here are some questions we're going to work on. Next slide. So the first one is really easy to answer. Why don't you just put it at L2? Well, this is the view from L2. That's the Earth, that's the sun, that's a partial eclipse of the sun because the sun, the Earth, and L2 are in a dead straight line. So James Webb would be in, the Earth would be eclipsing the sun continually, and that's bad for solar panels. They don't work very well. The other thing is that this is the sun's corona, and it's very hot. It gives off a lot of radio waves. So if you're trying to listen to a signal from Earth and you're in the blare of all this radio noise, it's very difficult to get a signal. Here's the moon, which is also a nuisance because it'll be zipping back and forth. So instead, instead of putting it at altitude, they put it at an orbit that's larger than the moon's orbit. So the Earth and the moon wobble around the sun from James Webb's point of view and don't block things. So that's one question crossed off. Next question. Okay, I'm going to give you a little primer on orbits. So first, two-body circular orbit. Two bodies, sun, Earth, could be Earth, moon, could be Mars, Phoebus. So you have a large heavy body and a smaller one. Smaller body goes around in a circle, around and around, repeating itself, which is the definition of an orbit. It's a trajectory that repeats itself. So circular orbit. Wouldn't it be nice if the universe was this simple? Next slide. In fact, most orbits are elliptical. They're a little kind of squashed circle. And in this case, the sun and the Earth. And the sun isn't in the center of the ellipse. It's slightly off to one side at one of the focal points. And that's a characteristic of the two-body elliptical orbit, which is still really easy to deal with because it goes around and around exactly the same. Period's always the same. Does that until the end of the universe. Unfortunately, life is not that simple because we have other bodies. And here we're introducing another one. We'll call that one Jupiter, and this sun and the Earth. And we're going to keep it far away so it doesn't mess things up right away. But it attracts the Earth with its gravity. So the Earth, instead of following the ellipse that we had in the previous slide, gets pulled off a little bit. So this is kind of a 2.5 body situation. So it's two bodies with perturbations. And this is the, well, go back to the one I'm not quite finished with. So this is the model. It's usually used when you're planning space missions. You know, that basically everything's behaving itself in an elliptical orbit with a little bit of strain from other planets. So this is kind of like standard orbital mechanics. If this third body is allowed to come in and play with the others, things get really messy. It goes totally chaotic. There is no repeatable trajectories, which by definition means no orbits. They're just buzzing around like a bunch of flies, and the Earth actually might get ejected from the whole system because it's so chaotic. So with three bodies in close proximity, you can't generate orbits. But under some conditions, you can. If you restrict the situation down to two heavy bodies and one light one, sometimes you can get regular orbits. The next slide. So this is an example of the type of bizarre orbits that can be created in a three-body situation. Three bodies, Sun, Earth, James Webb. James Webb is small, so it's not contributing anything to the gravitational fields. And that's the restriction we need to get any kind of sensible orbits. So here's three weird orbits. Halo orbit, horseshoe orbit. Here's the satellite reversing direction. Twice each orbit. It just turns around and goes the other way. Pretty weird. This is a near rectilinear orbit. That's the one they're going to use for the lunar space station, the Gateway project. So we'll concentrate on the halo orbit because that's the one that the James Webb uses. Next slide. So this diagram is in a rotating frame of reference. So I'll have to just digress a little bit, talk about frames of reference. Okay, for instance, right now, I'm standing still. That means I'm not moving in relation to our frame of reference. And our frame of reference is the walls and the floor and the world. And this is the frame of reference that we all share. And in this frame of reference, the laws of motion apply. I can play marbles. If I put a marble down, the marble will stay at rest. If I put it in motion, it will stay in motion. until it hits another marble, and it'll go off on an angle, but momentum will be conserved. If I swing a pendulum, it'll act like a pendulum. So all these laws of motion apply exactly the way we expect them to. If somebody's going over top of us in an airliner, and say there's a passenger waiting in line for the washroom, she considers herself to be standing still because she's not moving in relation to her frame of reference, which is the cabin of the aircraft. She could even play marbles. If she put a marble down on the floor, it would stay there. If she shot it, it would go in a straight line. Conservation of momentum, pendulum would work like it's supposed to. So all of the rules of physics work, even though these frames of reference are 500 miles an hour apart. Everything changes if there's rotation. If you put me on a merry-go-round, everything's different. I have to hang on to the pole because suddenly this centrifugal force has appeared that's trying to throw me off the turntable. I can't play marbles anymore. If I put a marble down at rest, it doesn't stay at rest. It just spontaneously rolls away. If I try to shoot it, it goes in a curved line. If I try to swing a pendulum, it doesn't go back and forth. It goes in circles because of the Coriolis force. So in rotating frames of reference, you need a completely new set of physics rules, and the old ones don't work very well. So in this diagram, we have a rotating frame of reference. It's rotating around the sun with the Earth. So here's the sun, here's the Earth, and the frame of reference is rotating as the Earth goes around the sun. So the horizontal line is spatial dimension, sun, millions of miles, Earth. The vertical axis is force. So force to the right, force to the left, and the blue line is centrifugal force. So if we put James Webb up here, it experiences significant centrifugal force because of this rotating frame. If we move towards the sun, the force gets less and less. On the other side of the sun, the force comes back, but now it's pointed in the opposite direction, so it's below the line. So you got that centrifugal force, increases with distance, decreases as we come to the center. But the centrifugal force isn't the only force out there. Next slide. Here we have the sun's gravitational force. And the sun's gravitational force is obviously always towards the sun. Out around the Earth, we have the James Webb telescope. It will feel the sun's attractive force, and it's graphed below the line because the force is to the left rather than the centrifugal force, which was to the right. And of course, it's not just the sun's gravity we have to take into account because the Earth has gravity too, which is in the next slide. So we've still got the sun's gravity, the green line. I put in the Earth's gravity, which is the red line. Same shape, but much smaller because the Earth is much smaller. And sometimes they work in opposite directions. For instance, at this point right here, if we put the James Webb there, it would be pulled to the left by the Earth's gravity, pulled to the left by the sun's gravity, and both those forces are exactly the same and cancel out. So if we put JWST there, it would experience no gravitational force. So now we've got the gravity figured out, we'll bring the centrifugal force back in again. So we'll get rid of individual Earth gravity and sun gravity. We'll keep the combined gravity and put the centrifugal force back in. Next slide. So here's the centrifugal force back again. Here's the sun's gravity and the Earth's gravity together. And once again, there are a couple of places where the centrifugal force and the total gravity are exactly the same but opposite. The L1 point and the L2 point, one on each side of the Earth. So if we put James Webb right there or right there, it would be completely balanced between the centrifugal force and the gravitational force. And they chose to put it out at L2 because if they put it at L1, then it wouldn't be a good place for observation and the Earth would be in the way and stuff. They put it out here at L2. Next slide. So of course, those diagrams were we just had kind of one spatial dimension. We're kind of curious about what's happening in three spatial dimensions. So this has three spatial dimensions. There's in, out, forward, back, up, down. And the dynamics of this circular orbit around the L2 point are very similar to the dynamics of a pendulum going in a circle. Here with the pendulum, the gravity is pulling straight down parallel to the axis. The string is pulling at an angle in towards the axis, and the resultant of those two vectors is this centripetal force pulling in towards the center, which counters the centrifugal force. If you take that pattern of vectors and kind of like turn it and flip it over, it's exactly the same for James Webb. You have a force at an angle back towards the axis, in this case, the gravity. You have a force that's parallel to the axis, in this case, the centrifugal force, and the resultant is a centripetal force towards L2. And that's why James Webb is orbiting around L2. It's attracted to L2 by this geometry of forces. Got it. Next one kind of illustrates this in a different way. So this diagram, we have two spatial dimensions, but kind of like a flat world. There's around and around, in and out. The vertical axis is gravitational energy. So it's like a contour map showing how strong the gravitational energy is at any point in this diagram. Sun, Earth, it could be Earth, Moon, but in this case it's Sun, Earth, because we're dealing with the James Webb. And you can see there's 5 points on this diagram that are flat. L1, 2, 3, 4, and 5, and those are the 5 Lagrange points. And what they are is they're places where gravity and centrifugal force balance each other out, and an object set there very carefully will not experience any forces. Unfortunately, it won't stay there because it's a saddle point. The best analogy is taking a marble and putting it in the middle of a saddle. If you're really careful, it'll stay there, but the first gust of wind, it'll roll off one side or it'll roll off the other side. So these are saddle points. So if the James Webb just drifts a little bit towards the Earth, it'll drift faster and faster and faster and faster. And it'll do it same in the other direction too. So the James Webb has to do this little kind of thing like every 6 months or so, or 6 weeks. It does like a little adjustment, just a tiny little bit of rocket thrust, just to ease it back into the orbit, because otherwise it'll just very slowly fall out. Next slide. So this starts getting really weird. This is kind of an Alice down the rabbit hole thing. Here's L2, here's the Earth. I'm going to be way over there somewhere. These spiral lines are lines of equal energy. Just like the previous diagram, there was those contour lines of equal energy. And so if you throw a spacecraft from Earth along one of these lines, it'll fall up and into the halo orbit. That's exactly what they did with James Webb. They picked one of these trajectories, threw it up there, and it just went into the orbit. If the orbit deteriorates, if James Webb drifts a little bit, what it'll do is it'll fall into one of these red trajectories and spiral back towards the Earth. Or if it goes off the other direction, it'll spiral out into the solar system. And if you add up all those trajectories, they form a tube, which in the trade is called a manifold. So it's a tube of equal energy trajectories, and the energy is equal to the halo orbit. So a spacecraft can move along any one of these without exerting any rocket thrust. Now you're probably just dying to find out what happens at the edge of the diagram here. So we'll look at the next slide and it will tell us. Gets weirder and weirder. So Sun, L2, sorry, Earth, L2, L1, Sun's way over there. This is a different diagram, you can ignore that one. So these exit trajectories merge into entrance trajectories for L1. And the exit trajectories from L1 merge into the entrance trajectories for L2. So you can take a spaceship that's orbiting this halo here, and just with a little push, just push it out of its orbit, and you can have it fall all the way over and go into a halo orbit around L1 without expending any rocket fuel. And if you look at the even bigger picture, so here's Earth, Sun, L1, L2, these trajectories extend out the other side. So it's possible to get a satellite to be in halo orbit, fall over to L1, fall around the sun, come back, fiddle around, over to L2, scoop around. This is the horseshoe orbit that I showed you earlier. That's why the orbit reverses direction. It's going in one direction inside the Earth's orbit and the other direction, the outside of the Earth's orbit. Now, the really weird thing is that these manifolds are not confined to the vicinity of Earth's orbit. There's manifolds that extend out into the solar system, and they tend to go from one Lagrange point to another Lagrange point. So for instance, from the Sun-Earth L2 out to the Mars-Sun L1. So you could get on with very little energy, you could go from L2, hop on this manifold, and just drift all the way to Mars virtually without firing a rocket. Okay, next picture. Last picture, actually. So this is kind of a representation of the solar system with all these manifolds snaking around. So you see, here's one planet, might be Earth, and there's Earth, Moon at a Lagrange point. And here's a manifold that goes off to Jupiter, but it goes really close to this manifold, which goes off to, I don't know. But if you were traveling along this manifold, where the manifolds come very close together, it requires almost no energy for the spacecraft to just kind of like step sideways and change manifolds. So you can start going off to Mars and change your mind and go off to Saturn. And these manifolds, they're not in a fixed location because the ends are attached to Lagrange points, and the Lagrange points are moving with the planets. So these manifolds are out there snaking back and forth and moving over the years as the planets move. But if you get into these manifolds with a spacecraft, basically you can go anywhere in the solar system with virtually no energy. And this may sound really far-fetched, like it may, like, you know, what's he going to do next? Talk about flat Earth stuff? No, this is for real. This is actually how spacecraft move in the solar system if they're not in a big hurry. So, for instance, the Apollo spacecraft, they followed one of those trajectories to the moon, around the back of the moon, and back to the Earth again. And they were just following one of these low-energy trajectories, just like these are. The James Webb followed one of those low-energy trajectories from the Earth up to L1. There's been lots of spacecraft that their missions have been designed to take advantage of these low-energy transfers. And I think this is the future of space exploration. I don't think it's Elon Musk's rockets. To do this, you can't take people on these routes, on these subway routes, because they're too slow. Humans are too impatient. They can't wait 2 years to get to Mars. They're too fragile and impatient. You can't spend two years basking in cosmic radiation. You need a big rocket to blast you there in 3 weeks. It's like taking a speedboat and just like smashing through the waves instead of surfing them. So I think in the future of space exploration is like James Webb, a great, big, clever, advanced robot that does a really amazing job. And we send it up there into this system of manifolds, and the robots go off and do things and do the exploration for us. It's cheaper and safer than having people there, and you can do all sorts of stuff that you can't do if there's people on board. So I think this is the future, and James Webb is showing us the way. And that's the end of the talk. So I invite questions. There's a bunch of names that have been put on them. Some people call them the interplanetary superhighway, the interplanetary turnpike. I think of it as the interplanetary subway because they're tubes and they have stations. you take the tube to this station and then you switch to a different subway line and go in a different direction. But what they are is they're mathematical concepts. They're collections of equal energy trajectories. And they don't have any physical substance, so they can go right through each other. They can cross. But if you're going to transfer between one and another, they have to be very close to being parallel or cross at a very shallow angle.
When take on the out system.
If you took one of the planets out, you take out its Lagrange points. So you take out 2 subway stations. So you'd still have the network, but it would be a smaller network. And if you whittled it down so that there was only one planet, then you would have that diagram with just Earth and the Sun and the horseshoe orbit. It wouldn't be connected to anything else. Question? Sorry? Yeah, that's something different. That's the wormholes are kind of theoretical and science fiction-y, and they're travel faster than light and take you across the galaxy in a blink of an eye and that kind of thing. And this is real. Wormholes are not necessarily real. Question? Well, this kind of field of orbital dynamics was first started in the 60s with the with Apollo. Because even something as simple as going to the moon, you can't do it with traditional orbital mechanics because it breaks down when you've got more than 2 bodies. So I'm not sure when it was first started from an academic point of view. I'm sure, like most things, start in academia a half a century before it ever arrives, on the launch pad. But this concept of low energy transfer orbit has been around for a long time. There was one satellite in, I think it was in the 80s, and it was a sun observation satellite. So it was put at the L1 point because it was looking at the sun instead of away from the sun. And after it had been there for a while, a comet came in, and they saw the comet coming and said, like, dang, we can get the satellite away from its L1 point and chase that comet and intercept it. And they did. And what they did is it left the L1 point, zipped around to the L2 point, did another little gravity assist, and went off and intercepted the comet. I mean, just an incredible dance of complex orbital dynamics. And I think that was in the 80s or 90s that they did that. Question? Right. For the orbit or for the telescope?
Like, was that where they could get the most information about something?
Yeah, it was kind of a blank spot in the spectrum. There's this big gap between Hubble and Spitzer that they just didn't have high quality images and information in. So that's really where they wanted the next space telescope to look at. And it, like I say, it's all a balancing act. Like if they didn't have as much money, they would have had a smaller mirror and less light gathering, or not as many cameras, or a lighter, smaller launch vehicle and stuff. So they did as much as they could. Well, this is kind of a generic solar system. Unless you identify the sun and Earth and L2, that's where it is. So if I mean, I don't know where the sun is. It looks like from the shadow that the sun's over here. So the diagram's wrong because there wouldn't be a Lagrange point there. It would be over here because it's in line with the sun. So this is kind of an artist's conception. Bruce.
Is there any connection between this subway, or whatever you want to call it, and this idea of that they sort of out there where they kind of go past a planet and kind of pick up speed. And
Oh, okay, that's-
slingshot,
yeah, that's a gravitational assist. Uh, it's. It's related in that it's a three-body problem that needs to be solved, has to be solved numerically. And it's a constant energy trajectory. Because there's usually there's no rockets involved. They just get it right on and it just goes and zips around. So it's related in that way. It's a low energy orbit. But it's kind of a separate topic. It actually blends in with this because, like, if you wanted to send something out to Jupiter, it takes a lot of energy to throw something all the way from Earth to Jupiter. But if you can drop it back to Venus and have it do one of those gravitational slingshots, you can shoot it so that it comes up and grazes one of these tubes and then enters the tubes and follows the tube. So the trajectories in space missions are usually a combination of orbital design. Part of it is traditional rocket blasting, parabolas and ellipses. Part of it is this gravitational assist strategy, and part of it is using these low energy transfers.
Bruce, it's my understanding of the gravitational assist technique. It's not a constant energy type deal because you're getting angular momentum transferred from the big body to the little body.
You're right.
And this is how you get it. For example, you get it out there, slowing down, approaching Jupiter. Here comes Jupiter. It falls in to Jupiter down the gravity well, turns the corner and comes back out, going just as fast, but now it's Jupiter's velocity as well. And Jupiter
correct.
slows down and the spacecraft speeds up.
Yeah, I was oversimplifying it. What I meant was that it requires no energy input from the spacecraft. It doesn't require a rocket burn.
Yeah, it's different from this
Yeah.
constant potential type thing.
Yeah.
When it's to L2, does it naturally start to make us which does it require Kate? You said that every so often we need to be pulled back in or
Right.
drifts around that goal.
Right. It was the momentum that it took with it. It followed one of those green line trajectories. It didn't get to L2, never went to L2. It went directly into the halo orbit around L2.
All the way.
Yeah. Yeah, it wasn't in the plane of the ecliptic. It did like an elegant little dance that came up from below and into the
Rotation.
yeah, and they were so clever about it.
The lasso.
Yeah. So there was a little orbital insertion push, but they're really little. Like the delta V, the acceleration to get it up from the Earth is like, like tens or hundreds of kilometers per second. The insertion burn was like 1 meter per second. It was just the tiniest little toot. You probably do it with a fire extinguisher, toot. And they were so clever with the designing the orbit that it just fell into not a circular orbit, but into this elliptical orbit that they wanted, so that it was lined up with the moon's orbit and larger in diameter than the moon's orbit. So the moon would never eclipse the sun. And the another little interesting factoid on this saddle business, where the marble can kind of roll one way or the other, there is actually wind pushing on it, just like the marble on the cowboy saddle. And the wind is the solar wind acting on that big, the sail area of the sunshade. So that there is actually physical pressure from light when it hits things. And that sunshade is about the size of a tennis court. So it's the size of a really large sailboat sail. And there's a significant amount of pressure against it. So that's trying to push James Webb away from L2, like away from the sun. So James Webb was put on the sunward side so that it's kind of like going downhill towards the sun, but the pressure of the light is keeping it from going downhill. So it's balanced closer to the sun, between L2 and the sun by I don't know how many kilometers.
It's whether they show how the data that they recovered a long time ago. The field around the earth was no electric, so distorted. We completed some forced beautiful all the time. Let's see. So visible to the sun, no the sun to energize the solar.
It's the sun is completely visible all the time. The mission design would not tolerate any eclipses whatsoever, even partial eclipses by the moon. So it's always fully exposed to the sun. But this is light pressure. It's not kind of solar wind. It's not particles. It's the actual pressure of the light itself, and that's quite uniform. The solar wind varies a lot depending on how active the sun is and what it's kind of spewing out, but it's always roughly the same brightness, so the light pressure is always the same. So the guys back on Earth here are constantly monitoring its position, and about every 6 weeks they do orbital maintenance burn and say, okay, like 2-second burn at this point in the orbit and give it a little adjustment. And that's what's going to determine the end of the mission, is when it runs out of propellant. Because once it runs out of propellant, it can't control the direction it's pointing, and it can't stay in its orbit, and it'll enter one of those the red ones, the red trajectories, one of the manifolds, and go off wherever it goes off to. It'll probably end up in a horseshoe orbit and have a really bizarre travels as the decades go by. What they're planning to do with it is when the fuel is really low, they're going to put it into a kind of a graveyard orbit. They're going to move it over and put it in the Earth's orbit, I think, following the Earth, just so that junk doesn't clutter up L2, because it's a really valuable location. I don't know if you remember that the diagram with the kind of like the humps and the contour lines. If you're trying to get away from Earth and out into the solar system, there's this wall of gravitational energy that you have to get up and over, but there's a gap in the wall, and that's where L1 and L2 are, and it's like a fence in the corral. So that's the place that you shoot for if you're going anywhere in the solar system. You want to exit the Earth Moon system through the gap at the Earth Moon L2 point. So remember that next time you're planning a space mission.